Hey everybody, welcome back. This is Jonathan Gardner. We're doing circular lengths basic mathematics. This is section 5.3, Pythagoras Theorem. And I'm going to give a spoiler alert. Well, it's not really a spoiler, but Pythagoras Theorem has to do with right triangles, right? And if the lengths of the legs of the right triangle are a, b, and c, then a squared plus b squared equals c squared. And that's the video. Congratulations. No. Really, what he does in this section is he plays a game with you, the reader. And the reason why he plays a game is he gives you just enough information that you can prove the Pythagoras Theorem on your own. So he's going to go through some formalities, some definitions. He has this long section in the middle where he talks about how much do you assume when you're doing geometry versus how much do you derive and what the right balance is. And he also gets into some breaking the fourth wall and talking about why he's writing a book in the first place. Things like that. So let's get through this. Let's have some fun with it. Let's not take it too seriously. All right. So we have 3 points in the plane. 3 distinct points. Yes, they were distinct points. If I could write. The points are P, Q, and M. And so now we have 3 distinct segments. The segment PQ, the segment QM, and the segment PM. Okay, so 3 segments. If we take these 3 segments together, right, then this defines the triangle PQM. We draw a triangle symbol, PQM. All right, what does that look like? So we have 3 points. We have P over here, we have Q, we have M, and then we draw between these 3 points 3 segments. I'm going to use a different color. Let's use a green. So between PQ, the segment PQ, between QM, the segment QM, and between PM, the segment PM. And this green thing is the triangle PQM. Okay. Now he's very careful and he spends, I think, a little bit too much space explaining in his remark on terminology here. He says the triangle is literally the edges here. It is not the insides. But in trying to come up with a name for the insides of the triangle, like we have disc for circle, mathematicians have proposed the word trisc, T-R-I-S-C, and that's a probably good name. However, people don't like that name. So if you go outside of mathematics and say the trisc, they're not going to know what you're talking about. There is a more formal word that we use. There's like a series of these shapes having to do with multiple dimensions. And this shape in 2 dimensions is called a simplex. So you might go out in the wild and you might see somebody use the word simplex. However, most people understand that the triangle is indeed these 3 lines, but the triangle is also the insides of the line. Okay. Now, conventionally or in practice, this isn't a problem because when we talk about the area inside and the edges, it's fairly obvious what part we're talking about, right? Now, we notice also that inside this triangle, each of these line segments has an angle. So there's an angle here, there's an angle here, and there's an angle here. Okay, you see those 3 angles? So if you just look at the ray MP and the ray MQ, you have an angle PMQ. You start at PM, you go to PQ using the right-hand rule counterclockwise. And so there's 3 angles inside of here, and there is a relationship between these angles. Okay, but before we go there, I'm going to talk about a right triangle. A right triangle is special because one of those angles is indeed a right angle. So this is what a right triangle looks like. This is the right angle. So this is a right angle, which is equal to 90 degrees, which is 1/4 of the full circle. And then we have 2 other angles. Okay, and so this is a right triangle. In a right triangle, we have the property that one of the angles is indeed a right angle. And so these lines are actually perpendicular to one another because of the angle between them. There is an assumption. He calls it RT. Okay, and he does not go into depth on why this assumption is true. He doesn't even bother proving it to you, but he does say that we're going to get to a point where we have enough mathematics based on very basic assumptions so where we can actually prove this for ourselves. So if we have two right triangles, and the triangles are called triangle PQM, and the other triangle is called the triangle P prime, Q prime, M prime. Okay, so 3 separate points, and they have legs, obviously. PQ, PM, and QM, and over here we have P prime, Q prime. We have P prime, M prime, and we have Q prime, M prime. So they have 3 legs. And the legs have equal length. That means that PQ is the length of PQ. How do we write that? Yeah, the length is equal to the length of P prime, Q prime, and the length of PM is equal to the length of, you guessed it, P prime, M prime, and then we can conclude, okay, one conclusion we can draw is that the corresponding angles are equal. No, the angles are not equal. The measures of the angles are equal. Okay, and B, we can conclude that the areas are equal. Areas of the triangles are equal. And C, we can conclude that the length of QM is equal to the length of Q prime, M prime. Okay, what does it say? This is a fairly involved exercise, but QPM over here, and then over here we'll have a different triangle. I'm trying to make it equal, but I'm not very good at it. Okay, suppose that they were equal. Okay, so we have this triangle here, and we have this other triangle here, and this one is too big, so I'm going to make it smaller. I'm going to try to keep these 2 triangles equal. So we have triangle QPM, or PQM, triangle PQM. Let's say P is that right angle, Q and M, and over here we have the triangle P prime, Q prime, N prime. So P prime, Q prime, and M prime. Notice that these 2 triangles are in different areas. This one's over here, this one's over here. They're rotated from each other, but otherwise they look the same. And indeed, if we can prove that PQ and PQ, P prime, Q prime have the same length, and that PM and P prime, N prime have the same length, then if we can show that, then we know that all the angles are equal. These are right triangles, right? So one of these angles is a right angle. Then we know that the remaining vert length is the same, all the angles are the same, and the areas are the same, okay? And you may recognize that this is the notion of congruence, but we're not talking about congruence quite yet. Congruence is a bigger topic. It's an important topic. It's a fun topic, but we're not quite there yet. Okay, this is a discussion that I think is interesting. On the bottom of page 122, that bottom paragraph. So he talks about how when you're teaching mathematics or when you're proving something in mathematics, you always have to start with a set of assumptions. On the one hand, you can try to assume the minimum possible, and then based on those minimum assumptions, build up a set of theories that gives you the foundation to prove the final theory, right? So what that would look like is you would have some assumptions down here, and then you would build up your, like, I guess your first floor of theories, and then you would get up here to your final theorem. Okay, and maybe there's like floors in between, right? Okay, and he says you can do it this way. The thing is, though, is sometimes the area of the work that has to be done to get you to a certain level of proof is a lot of work. And so what he says he does instead is, yeah, sure, he might take one of these fundamental assumptions, but he's going to take this one here, and he's going to take this one here, and he's going to take this one all the way up here, and maybe another one of these, okay? And then he's going to prove the final theorem based on these. And the reason why he chooses these ones, these, which could be proved, but, you know, he's assuming them, these things that could be proved. And the reason why he's doing that is because A, these are psychologically pleasing, okay? So he's basically saying, assume this is true because it makes sense in your mind. You can't really understand why it's true in mathematics, but it seems obvious, right? And so we're gonna take them because they're obvious. Second thing is, I don't wanna spend time proving all of this junk underneath these guys to get to these guys, right? Because that's not the point, and that's a distraction. Okay. On the other hand, he doesn't want to assume things that aren't completely obvious, right? If it's not completely obvious and he assumes it, then you might think that he's trying to pull a fast one on you. He's not really using full mathematics, or he's using some subset of mathematics, or maybe he's not even using logic at all, but something else. Okay, that's an interesting discussion to have. It's somewhat humorous, but the remaining part of this lecture, of this lesson, we are going to make some of these assumptions, and then we're going to prove the rest. So we're going to cover all the stuff that we need to prove to build up to the final theorem. And we're going to assume a great deal. So you're going to be exposed to half of the stuff that is some kind of proof, and we're going to skip half of the other stuff, right? So just kind of, you know, fasten on your seatbelts. Let's have some fun. Okay, so let's talk about what a rectangle is. Okay, and you probably know what a rectangle is because you've seen them before, but let's talk about them formally. Let's say that we have this assumption that says that if we have two lines that are parallel, so I'm going to write this down here, we have L and L prime are parallel. Okay, and then we have points P and Q, distinct points on L. Okay, and then we have KP and KQ be perpendicular to L through P and Q respectively. Okay, what does that look like? So we have two lines that are parallel, and parallel lines will never touch. That means that they are a certain constant distance apart, and I'm not really, these are probably not perfectly parallel, but they're pretty close, okay? Good enough for government work, right? And so we choose on these, we choose some point P and we choose some point Q, and then we draw perpendicular to these another line and another line. So this is L, this is L prime, and this is KQ, and this is KP. And then we know that these perpendicular lines intersect with the second line. So now we have this point Q prime and P prime. And I could write that out for you. It's a lot of words. So then we have points P prime, Q prime intersect L prime and KP, KQ respectively. Okay, so we have 4 points. Okay, the interesting conclusion that we have is that this distance, the distance from Q to Q prime, is exactly equal to the distance of P to P prime. Okay, and this is, we're doing this by assumption, right? We're just assuming that these two distances, so this is the distance from P to P prime, and this is the distance from Q to Q prime. Okay, and these two distances are the same. And if you take this whole thing and you rotate it 90 degrees, well, then that means that the distance here, the distance between P and Q, is also the same as the distance between P prime and Q prime. These two distances are the same as well. And this is a rectangle. Okay, so the rectangle is defined by 4 points with the property that the opposite sides are parallel to each other. And because the opposite sides are parallel to each other, then the opposite side lengths are also parallel to each other. But the proof is that you take these two sides parallel, you find perpendicular whatever things. Oh, also their angles are 90 degrees. Everything is right angles to each other. That's what a rectangle is. Okay, moving right along. Okay, and we can define a rectangle. The area of a rectangle, let's use black. The area of a rectangle is equal to AB, where A is the length of one set of opposite sides, and B is the length of the other set of opposite sides. What does that look like? Well, we have our rectangle, and we have these opposite sides of the same length, and these opposite sides of the same length. Let's call this one A, and let's call this side B. We could have also done it the other way. We could have said this is A and this is B. Doesn't matter, the area is the same. Okay, so the area is the product of the lengths of opposite sides. Okay, a square, obviously, you know what a square is. In a square, the length of A is equal to B, and so the area is just the length of one side squared, right? So you don't have to worry about pairs of opposite sides or anything like that. All right, next little theorem that he's going to prove is he wants to prove theorem 1. This isn't completely obvious. He says in a right triangle, measure of A plus measure of angle B is equal to 90 degrees where A and B are the non-right angles. Okay. All right. The reason why that is, how does he prove that? We conclude the two triangles must have the same area. Oh, yes. The reason why that is if you take a rectangle and then you draw a line down the middle here, okay, it's fairly obvious. This is one right triangle, this is another right triangle, okay? It's also obvious that this side is the same as that side, and this side is the same as that side. Therefore, these two triangles are congruent, and using RT, we know that, of course, this is the same length, right? And so this angle here is the same as this angle here, and this angle here is the same as this angle here. And if you look at it, then these two angles, A plus B, the measure of angle A plus the measure of angle B, must add up to this 90-degree corner. And that's why theorem 1 is proved using rectangles, okay? Theorem 2, let's actually do theorem 2 on the same page here because it's going to use the same picture. Theorem 2 says, and he's not assuming this, he's going to prove it to you. It says the area of a right triangle is 1/2 AB, where A and B are the legs. Okay, and the C is the hypotenuse. It's opposite the right angle. Okay, and how does he do that? Well, if this is length A and this is length B, okay, then this is length B and this is length A, then these two triangles added together equals the same area as the rectangle. And so since there's two of them and the area of the rectangle is AB, then each triangle must have 1/2 AB. And this is also 1/2 AB. So the area of a right triangle is 1/2 AB, where AB are the legs, the sides next to the right angle. And the hypotenuse is the other one. We're not using that to calculate the area. The hypotenuse is opposite the right angle. Okay? So those are two proofs that we have. And now we're ready to prove the Pythagorean theorem. Okay? In order to prove this, we're going to draw a big square. And then inside this big square, we are going to draw a smaller square. And this is, I'm going to do the best I can. Okay, now this isn't perfect, but this is length C. Okay, this is length B. And this is length A. Okay, you can tell that it's a bigger square on the outside because the sides are AB. So the area of big square that is A plus B squared, which is equal to A squared plus 2AB plus B squared. We learned that in the first chapter. That's how we square sums. And the area of the small square that is just c squared. Okay, so we have this small square on the inside here and this big square on the outside. And notice that we have 4 triangles, and if I were perfect, these triangles would be perfect as well, but I'm not perfect. So the area of the triangles here, this is 1/2 AB, 1/2 AB, 1/2 AB, 1/2 AB. It shouldn't be hard to prove why that is so. These are right angles over here. And the last little bit, so we say if we take the c squared plus 4 of these 1/2 ABs, that is going to equal to a squared plus 2ab plus b squared. You see that? All right. Again, the small square plus 4 of these rectangles is going to equal the area of the big square. Now, 4 times 1/2 AB, that's just 2AB. And we have a 2AB over here. These two terms will cancel, and you're left over with C is equal to a squared plus b squared. We proved the Pythagorean theorem, okay? This is a proof of the Pythagorean theorem. There are many proofs of the Pythagorean theorem. They are fun to find, they are fun to understand. So I hope you enjoyed that exercise. We're not done here, okay? The last little bit is when he starts talking about how we can apply the Pythagorean theorem. And this is, to me, having done so much with the Pythagorean theorem, this is pretty simple, right? But let's walk through this. So he says, let's say we have the diagonal of a square whose sides have length 1. What is the length of a diagonal square whose sides are length 1? So we have 1, 1, and we have this diagonal. The question is, how long is that? Well, we know we have a right triangle on here. And so we say 1 squared plus 1 squared, 1 squared plus 1 squared is equal to that diagonal c squared. So 1 plus 1 is 2 is equal to c squared. So c has to equal the square root of 2. So the length of the diagonal is the square root of 2. We've used the Pythagorean theorem to prove that. Okay. What about a rectangle whose has sides lengths 3 and 4? What is the diagonal there? So we're going to take 3 squared. We're going to add 4 squared, and we're going to get the diagonal length squared. Okay, 3 squared is 9, 4 squared is 16, 9 plus 16 is 25. So c is equal to the square root of 25, which is just 5, because 5 times 5 equals 25. And when we're taking the square root, it's always a positive, it's not the negative. And besides, negative lengths make no sense. So the length of that diagonal is 5. Okay, so these are 2 important triangles to remember. One important triangle to remember is 1, 1 square root of 2. Another important triangle to remember is 3, 4, 5. There is a whole bunch of these that are like this, that have integer relationships between the sides and everything like that. You can look it up on the internet. I'm not going to tell you the pattern. It's pretty fun. All right, another example. One leg of a right triangle has length 10 inches. The other length of the hypotenuse has length of 15. So we have 15 inches, we have 10 inches, and the question is, how long is this side, right? So we have 10 squared plus b squared is equal to 15 squared. So we have 100 plus b squared is equal to 125, or is that 225? That's 225. So we have b squared is equal to 125, so b is equal to the square root of 125. Okay. So this is the length is square root of 125. Okay. Perpendicular bisectors. Let's talk about them. They're interesting. They're fun. Let P and Q be distinct points in the plane. So P, Q are distinct points in the plane. Let's put an S on the end there. Okay. We recall that the perpendicular bisector of the segment PQ, so the perpendicular bisector of segment PQ is the line perpendicular. It's perpendicular to PQ, or rather the line PQ, and it's also halfway between. P and Q. So graphically what that looks like. So we take 2 points, P and Q. We draw the segment through there, and we find a line that passes through the midpoint and is perpendicular. So the midpoint M and is perpendicular. And this line is called the perpendicular bisector. It's perpendicular to the line. It also bisects, cuts in two even parts, okay? If O is any point on the line passing through P and Q, so he actually uses O here. So he notes that the distance between P and O has to equal the distance between O and Q because it's halfway through. I used M, he uses O. Use O. So O is on the segment between P and Q. How do we know that O is on the segment between P and Q? Because the distance between P and O plus the distance between O and Q has to equal the distance between P and Q. Okay? You see? This is from the previous section when we discovered that points on a segment have a distance that's between the length of the segment and 0. Okay? And in this case, there's 2 of them that has to equal the sum, and these 2 guys are equal to each other. So this is 1/2 the distance of P and Q is equal to the distance of P and O. Okay, so distance between P and Q, it's halfway through. All right. This next result is important. It says that if we have M is on, and I really screwed that up by calling that M. We have a point M on the perpendicular bisector somewhere, okay? Then this corollary says that the distance from P to M on that perpendicular bisector is always equal to the distance from Q to M. So that says that the distance between P and M is the same as the distance between Q and M. And graphically, it should be relatively obvious why this is so. Because you have this, it's perpendicular, which means these are 2 right triangles, okay? The lengths here are the same. This is the same segment, right? And so these 2 lengths must also be the same using RT. So it's pretty obvious. By Pythagorean theorem, though, remember the Pythagorean theorem is based on this idea that those 2 right triangles are the same right triangle. The Pythagorean theorem says that we take the 2 legs, so we have the distance from O to M, we square that, and we add the distance from P to O, and we square that, and that's going to be the distance from P to M squared. And for the other side, the distance from O to Q squared plus the distance from Q to O, wait, we already did that, distance from P, O to M, yeah, distance from O to M as well. So this is that leg here, and then we have the distance from O to Q. O Q squared has to equal the distance from Q square to M squared. And so if we can prove that these 2 things are equal, then we can prove that those 2 lengths are equal. These are equal because they're the same. These are equal because it's the bisector, and so therefore these 2 things have to be equal as well. That's pretty much all there is to that. You can read the more formal mathematical language he uses. Let's go over really quick some of the exercises. The first exercise is how do you calculate the length of the diagonal of a square? And he doesn't draw a picture here, but I will draw a picture. This should help you understand how to solve this problem. So if we had a square whose sides are 2, and then we had the diagonal, how would we calculate the length of that diagonal? Let's call that diagonal C. Well, C squared is going to be equal to A squared plus B squared by Pythagoras theorem. But the lengths of the legs are 2. So we have 2 squared plus 2 squared. 2 plus 2 squared is 4. 2 times 2 is 4, so we have 8. So C squared is equal to 8. So C would be the square root of 8. So I basically did 1A for you. The rest are pretty easy as well. There's a pattern there. You'll find it really quick. And when you're solving for R, you just plug in R and you get C is equal to something, square root of something R. Okay, number 2, what is the length of the diagonal of a rectangle whose sides have lengths 1 and 2, 3, and 5? You can draw out the rectangles for yourself. Same thing, find the diagonal. What is the length, number 3, of the diagonal of a cube whose sides have length 1, 2, 3, 4, and R? Hint, first compute the square of the length. Consider the diagonal of the base square of the cube and apply the Pythagorean theorem twice. This is hard to see in 2 dimensions, let me try to explain what they do. So imagine I'm looking, so we have this cube and I'm looking at perspective in it, right? So I'm kind of looking like towards the corner of it. So here's the bottom, okay? Now, if I were to calculate this diagonal here, okay? And then I were to consider the shape who has a length here, this diagonal, and then it goes from here to there, okay? So I first calculate this diagonal, and then I calculate, we have a rectangle with side here, side here. This is the diagonal of the cube, okay? In practical terms, let's do a number that they're not doing. Let's do 7, because 7 is nice and complex. So the diagonal here, this diagonal on the bottom, this will be the square root of 2 times 7 squared, right? And then this diagonal here, this one right here, this will be the square root of 7 squared plus 2 times 7 squared. So this is equal to the square root of 3 times 7 squared. Okay, you see how that works? I used this length squared. Square root of the square of a square root is just the number itself. I take 7 squared, I add them together and take the square root of that to get that length. Okay. What is the length of diagonal and rectangular solid? Pretty much same thing except you're not using cubes. And 5, what is the length of the diagonal of a rectangle solid whose sides have length A, B, and C? And he says, what if you multiply the sides by the factor R? What is the new length? Okay. For that problem, you should expect that the length would also multiply by a factor R. So your answer to the first one is, the answer to the second part is R times the first part. You should be able to show that. 6, you stand at a distance of 500 feet from a tower and the tower is 100 feet high. What is the distance between you and the top of the tower? So that's just a problem here. You have 100 and you have 500. What's the distance there? Straightforward. 7, in a right triangle, one side has length 7 and the hypotenuse, that's the side opposite the right angle. The hypotenuse has a length of 10 feet. What is the length of the other side? And that's just, you're gonna plug in, you're gonna have a squared plus b squared equals c squared. So you know this one, you know this one, you have to solve for this one. That's what's saying there. Pretty straightforward. 8, you are flying a kite. Assume the string between you and the kite forms a straight line segment. It doesn't in real life, but assume that it does form a straight line. Suppose the string has a length of 70 feet. A friend of yours stands exactly below the kite and is at a distance of 30 feet from you. How high is the kite? So he's standing 30 feet away from you, and the kite string is 70 feet, and he's standing directly below the kite. So how high is the kite? Write down in detail the similar steps left to the reader in the proof of the corollary to the Pythagoras Theorem. So he's talking back to the corollary of the Pythagoras Theorem. Write down, he just wants you to write that down in your own words in detail. Don't skip anything. And 10, prove that A, B, and C are the angles of an arbitrary triangle. Then the measure of angle A plus the measure of angle B plus the measure of angle C equals 180 degrees. Use the following method. From any vertex, draw the perpendicular to the line of the opposite side, then use the result already known for the right triangles and distinguish the 2 pictures in figure 3.1. So there are 2 cases. Basically, you have triangles. We already have right triangles, right? You have triangles like this, where you drop a perpendicular, and we have triangles like this, where you have to extend this line out, and then you drop a perpendicular. The question is, how do the angles relate? What is the sum of all of the measures of the internal angles in these cases? You have to solve both cases separately. 11, show that the area of an arbitrary triangle of height h and a base whose length is the area of an arbitrary triangle of height h whose base has length b is bh over 2. Okay, and the base is the length of this part of the triangle that is below is where the perpendicular guy drops down to. Okay, so this is the length of the base. This is the height. So this is the base. This is the height. This is the height. This is the base. And show that the area of that triangle has the area of 1/2 BH. Okay. And 12, show that the length of a hypotenuse of a right triangle is greater than or equal to the length of a leg. Okay, that you can use the triangle inequality from the first section. and let P be a point and L be a line, show that the smallest value for the distance between P and M, between the points P and the points M on the line is a distance dpq, where Q is the point of an intersection between L and the line through P perpendicular to L. This one is confusing. I'm not going to lie. It's really a simple problem, but understanding what it's saying. So you have a line L, and then you have a point P. Okay. Now you can take any point along this line. Let's say this point M here, and you can calculate the distance to that point. Okay. Now there is a minimum value for what these points can be, and that minimum value happens to be at this particular point Q, which is on the perpendicular between P and line L. So you have to show that that is the minimum length, that any other point M will have a longer length than the distance between point P and Q. 13. This exercise asks you to derive some standard properties of angles from elementary geometry. They are used very commonly. We refer to the following figures. So I'm not going to give you much help there. You need to study and look at these pictures and figure out a pattern to solve them. They are fun. They are easy. They're not hard. And this is why I think often textbooks on geometry go too far and say too much. And lastly, last question, number 14, let triangle PQM be a triangle. Let L1 be the perpendicular bisector of segment PQ. And let L2 be the perpendicular bisector of QM. Let O be the point of the intersection of L1 and L2. Show that the distance between O and P is equal to the distance between O and M, and hence that O lies on the perpendicular bisector of PM. Thus the perpendicular bisectors of the sides of the triangle meet in a point. Oh, it's not hard. P, Q, M is a triangle. Perpendicular bisector, perpendicular bisector, perpendicular bisector. They all happen to meet at a single point. Show that's true. This triangle is not, I'm not very good at do they all? And hence the O lies in a perpendicular bisector. Thus the perpendicular bisectors of the sides of the triangle meet in a point. Yes. So you basically have to show that this point is where they all meet. There is a point that is common to all of the perpendicular bisectors. How do you calculate the perpendicular bisector? How do you calculate the distance between the corners of the triangle and the perpendicular bisector? That is the question that we answered already in this section. You're going to use that to do this proof. Anyway, I hope you guys enjoy this section. I hope you take some time to enjoy these problems. I hope that you internalize the proof of the Pythagoras Theorem, and not just that, but the applications of that proof. Take care, guys. Have a great day. Bye-bye.
Hey guys, thanks for watching this video. This video is part of my series on Sergey Lang's Basic Mathematics. You can click here to watch the rest of the videos in the playlist. You can click here to learn more about me, and you can click here to support my channel. Thank you so much. Bye-bye.